Hey, everybody. Thank you. All right, so I'm really happy to be here. Thank you for having me. It's true, there's a Chrome guy at an SEO conference. I didn't get lost on my way here. So my team is responsible for maintaining all of the documentation and best practices around the metrics, tools, and APIs to help make the web faster. And that includes all of you in the SEO community, because web performance and SEO have one very important thing in common, and of course that's the core web vitals, thanks entirely to the page experience ranking signal in Google search. So I got to see that firsthand earlier this year when we launched interaction to next paint as the new core web vital metric, replacing first input delay. As I was monitoring the launch, I couldn't help but notice all of the support from the SEO community helping to raise awareness about the launch, and also all of the best practices to improve this new and unfamiliar metric. And when we look at the data, I really do think that that had an immensely positive effect on INP pass rates. So in the months leading up to and after that launch, we've seen INP go from something like 65% of sites having good INP on mobile to now it's more like 76%. So thank you all for your help with that. Also, the fact that you're having me here speaking to you today, I am so grateful for the opportunity, and also so that we can explore some of the common ground that we have between the web performance and SEO communities. While the core web vitals and page experience signal may very well just be one small part of the ranking factor, there are so many more reasons to care about web performance. So what I hope to convince you all of today is that your efforts to improve core web vitals will have an impact that goes well beyond SEO. One of the most illustrative examples I could give you about the value of web performance is the story of Project Feather. In December 2009, Chris Zacharias was working as an engineer at YouTube when he got fed up with how heavy the video watch page had gotten. It was over 1,200 kilobytes, and his goal was to make it under 100 kilobytes. He named the project Feather. He managed to get most of the way there by cutting down on just down to that core functionality of the page. Just the video player, only a few comments, and only a few of those recommended videos in the sidebar. And you might also remember that back then, videos were played using the Flash player. But just a few months earlier, the HTML5 video player had launched, and he switched over to that player, finally getting him down to just 98 kilobytes. So he finally met his goal, and Feather was ready for live traffic. He wrote up a blog post, invited people to start using it, and his hypothesis, like any reasonable person would expect, was that a lighter watch page would lead to faster experiences. Well, about a week later, he looked at the data and he was wrong. Performance had actually gotten worse. And as he wrote in a blog post a few years later, my worldview was shattered. Nothing made sense. So the results only started to make sense when a colleague thought to slice the data by geography. What he found was a disproportionate increase from users in places that you would tend to think of as having poorer connectivity or lower-end devices. For these users, it took actually more like 2 minutes to load this Feather watch page, which doesn't make sense until you look at their experience on the default watch page, which was more like 20 minutes. So to them, this new experience was so much better, proving that performance is relative. You can go from having a slow experience to a slightly less slow experience, and it would still deliver an immense value to the users. So Chris's experiment suffered from sampling bias, but the thing I want you to take away from this is not how to properly set up an A/B test. The thing about Feather is that it lowered the barrier to entry for users. In this case, performance was more like an enabling feature, the same way that accessibility is. And I know that YouTube is kind of a special example. It's the most popular video website on the web, And not everybody can just throw away 90% of your page weight as an experiment. So let's look at another case study, Sunday Citizen. They're an e-commerce site that specializes in bedding for the home. Vice called them the goat of weighted blankets, for what that's worth. And a couple of years ago, they collaborated with Shopify to improve their web performance. And I'm just speculating here, but I think it went something like this. They noticed that their core web vitals were not as good as they had hoped, and they reached out to the Shopify team to find out, is it something on their end, or is it something on the platform's end? And so the Shopify team took a look, and after some investigation, they found a few opportunities for improvement. And if I'm being honest, there was nothing groundbreaking here. They didn't have to re-architect the site or do anything major. The improvements that they did were pretty basic. So they moved some static resources onto the Shopify CDN, like render blocking, CSS, JavaScript, and fonts. They made the LCP image more discoverable by taking it out of CSS from a background image just to a plain old HTML image tag. And they made sure not to lazy load it. Instead, they added the fetch priority equals high attribute to prioritize it. And they also made some improvements to layout stability by reserving space for contents that shift layout on the page. And as straightforward as these changes were, they saw a 25% improvement to their LCP and a 61% improvement to their CLS, layout stability metric. But that's not the end of the story. When they looked at their business metrics, they saw a 4% decrease in bounce rate, a 4% increase in add to cart, and a 6% increase in their conversion rate. And if they looked at their revenue and reported that data, I'm sure that went up too. So this is another really great case study to show that there are effects on improving performance that go way beyond just SEO and getting people onto the site. It's about keeping users on the site and making them happy, because happier users will deliver more value for the site in terms of business metrics. So the ways that YouTube and Sunday Citizen improved their web performance followed some pretty basic web performance best practices. And as it turns out, the Chrome team has established what we've determined to be the most effective best practices for improving core web vitals. So now I'd like to change gears a bit and look at each of the core web vitals metrics and the most effective ways to improve them. But first, I need to confess something to you all. I'm a Chrome guy in a room full of SEO experts, and I'm feeling very judged with my headings on my slides. It's very basic stuff, so there we go. That's much better. So I present to you the 9 ways to boost your web performance speed in 2024, the ultimate guide to core web vitals near me. Let me know if I'm doing this right. All right, so let's start with LCP, largest contentful paint. I think most of you are familiar with the metric. Can I see a show of hands? Who knows about LCP? All right, I'm going to skip over the basic stuff, but I do want to go into a bit of detail because LCP happens to be the metric that the fewest websites have good scores on. So I'm going to spend a little bit more time on this, looking at a few special considerations, how to measure it, and then we'll get into the most effective ways to improve it. So LCP, like you all know, it's the largest piece of content on the page. It's important to remember, though, that there may be multiple LCP candidates as you go through the page load. Usually text is the first thing to appear, so maybe something like your H1 element is going to be the initial LCP candidate, and then you have something like a hero image pop onto the page. That's the new LCP candidate. But what you also need to keep in mind is that the LCP metric stops measuring after the first user interaction. So you can imagine if a user clicks or scrolls or types on the keyboard after that first H1, that's the final LCP candidate. So you might see different metrics depending on how the users behave. There's also some types of content that does not count as the LCP, the first being background images, like full screen background images. So these are things that the user would tend to consider more like decorative than content, so it doesn't count. The second thing is invisible content. This is straightforward. If the user can't see it, it doesn't count as content. But there's a gotcha here that sometimes content fades in, and what LCP is looking at is the initial opacity of that content. So even if it fades up from 0, the fact that it was initially 0 makes it not an LCP candidate. And the third thing is placeholders, like image placeholders, the gray boxes that you see as images are loading. This is great for layout stability, but again, this is not content. It does not count as the LCP. It's also a bit complicated because the biggest piece of content for you might be totally different for someone else. So the most dramatic example of this is somebody on a very wide desktop screen and somebody on a very narrow mobile screen. They're going to get different types of LCP contents. Maybe on a large desktop screen, wide images that are in landscape mode count as the biggest content. But as you shrink that screen size smaller and smaller, now it's responsive and it takes up a relatively smaller proportion of the screen. But at the same time, maybe you have paragraphs of text or a heading. Now it starts to wrap onto more lines. So now the area of that content is larger than the image, making it the LCP candidate for that page. Also, web applications are being built in ways that the standardization groups had never anticipated. So on a traditional website, each navigation requires a new HTML resource to render the next page. And then each page view starts from scratch. It resets the performance timeline, and then you get new LCP elements. However, single-page applications, or SPAs, they're all about reusing existing contents on the page, updating only what has changed. So as you navigate to a new page, instead of discarding that old page and getting entirely new HTML, you keep the skeleton of the page around and dynamically swap in those new contents. But the problem is that the performance timeline is going to keep ticking. The LCP element already happened earlier in that session. You do not get a new value. So as a consequence of that, there's only one LCP value for the entire session on that LCP site. And the Chrome team is aware of this. It's a pretty big blind spot in Core Web Vitals, especially considering how popular SPAs have become. We are experimenting with a couple of origin trials to fix this, but the important thing to remember for now is that SPAs are measured differently in Core Web Vitals. So if you've ever used the performance panel in Chrome DevTools, you've seen something like this. If you're not familiar with it, this is the trace view, and we're looking at the network track, showing you the order and the timing of resource loading in what's known as a waterfall diagram. And using this view, you can more easily see how resources can actually depend on each other. But I'm going to provide a simpler version of this just to go through a few examples for different LCP concepts. In these diagrams, each resource is color-coded, where you have blue for HTML, purple for CSS, green for images like the LCP image, orange for JavaScript, and red for fonts. So using this diagram, let's look at a hypothetical LCP and see why it might be slow. The best way to do that is to break it up into phases. And there are 4 phases for LCP. They never overlap, and between them, they account for every single millisecond of the LCP time. Each phase is also defined so that if one of them is the slowest, that gives you a clue as to what the problem might be and also what the potential fixes for that could be. And the first phase is time to first byte, or TTFB. Some people might think of this as the backend time or the server think time. TTFB also accounts for all of the time just to get to the server. So this is all of the networking stuff that happens along the way, like redirects, resolving DNS, negotiating TCP or SSL. And you could, if you needed, also break the TTFB time down into these sub-phases to get a better look. So that brings us to the #1 most effective way to improve Core Web Vitals, and that is to aim for instant navigations. Because the absolute best way to improve TTFB and LCP as a whole is to be completely 100% independent from network requests. So there are 2 ways to achieve instant navigations: restorations and speculations. You can think of them like optimizing based on where a user has already been and where they're about to go. A restoration takes a page that has already been loaded and already been rendered, and it serves it back to the user upon request in its already rendered state from cache. And a speculation takes a page that we think a user is about to navigate to, and it prefetches and pre-renders that in the background. History restorations are made possible by the browser's back-forward cache, or BF cache. You can think of it like taking a snapshot of the page as soon as the user navigates away, storing it locally in memory for later. And if the user eventually clicks back or forward to return to that page, the browser can simply paint the same pixels back onto the screen exactly where the user left them. So this is kind of a huge deal because 1 in 5 navigations on mobile are back-forward. And we know that mobile experiences are much worse than desktop. So this is a great opportunity to flip some slow experiences to instant ones. And the second trick to instant navigations is to speculatively pre-render the next page that a user is about to visit. And this is made possible with the Speculation Rules API. It's available now in Chromium-based browsers. A speculation rule is an instruction to the browser that says which links to pre-render and when. You do need to be kind of strategic about this, though, because there are limitations to how many pre-renders you can have at any given time. So the best way that you can make sure that you pre-render the most likely page a user is about to visit is to look at your analytics. Take that one link and eagerly pre-render it on the page. Something else to watch out for that causes slow TTFB is redirects. The problem with redirects is that each one of them is an extra, unnecessary hop before arriving at the final content. A user might be redirected from HTTP to HTTPS, or example.com to www.example.com, or if the content has moved, they go from /old to /new. Even external link shorteners like Bitly and Twitter's t.co, they actually work by introducing redirects. So they slow the page down. The way to mitigate this is to ensure that the links point actually directly to that final URL that the user is going to visit, whenever possible. It's not always possible. But the best way to find out if your site has a problem with redirects is to measure it. And I'll get back to measuring in a little bit later. For now, though, our second most effective way to improve Core Web Vitals is to use a CDN. CDNs are content delivery networks, which means that they have a fleet of edge servers all around the world. And by moving resources physically closer to your users, requests can be handled much more quickly. CDNs also make it easier to enable other performance features at scale, like caching, compression, and also the latest versions of the networking protocols like HTTP and TLS. And one CDN in particular, Cloudflare, actually just introduced a service last month called SpeedBrain, and that adds speculative pre-rendering to all sites on their free plan. So by using a CDN, you can attack performance from lots of different angles. The second LCP phase is the time from TTFB to the start of the request for the LCP resource, which is called the resource load delay. This phase only applies to image or video-based LCP elements. Text-based LCP elements aren't associated with external resources. So in those cases, this phase is set to 0. The third most effective way to improve Core Web Vitals actually has 2 parts. The first one is about discoverability. Remember from the case study with Sunday Citizen where the LCP source was hidden away in a CSS file as a background image? Well, that has a couple of really negative effects on performance. So for one thing, the browser has no idea that the image even exists until it loads and parses the style sheet, so there's no way for it to preload the image. You could declaratively preload that image manually using something like a link tag. But even if you do that, you'll run into the second problem, which is that the style sheet is still the bottleneck. The browser has nowhere to put that image, even if it's already loaded, until the CSS tells it to make it the background image for some element on the page. Also, for what it's worth, client-side rendering on the initial page load basically has the same issues, except it's JavaScript as the intermediary instead of CSS. But the solution in both of these problems is exactly what Shopify and Sunday Citizen did, just moving it out of the CSS and into the HTML using a basic image tag. It really is that simple. Another performance issue related to discoverability is lazy loading. The loading equals lazy attribute is LCP poison. Do not use it. It is bad. It prevents the browser from eagerly loading the image as early as it could, because it first needs to make sure that the image will appear within the viewport. And that's not always a quick process. Maybe the only thing worse than loading equals lazy is the data source attribute, because that's an indicator of a custom solution built in JavaScript. And custom solutions are strictly slower than native ones. And just to be clear, lazy loading is good. You should use it, but only for content that's below the fold. Only for content that's not critical. The LCP element is by definition critical, so it should never be lazy loaded. All right, so I said this was a two-parter, and part 2 is about prioritization. Even if the image is discoverable in the HTML, it still might not load as early as it could if there are lots of other higher priority resources on the page. Chrome assigns images a default priority of low. And for the first 5 images, it bumps it up to medium. But if you have critical render blocking static content like CSS, JavaScript, fonts, those have high priority. So you could actually be competing with those resources for network. The fetch priority equals high attribute hints to the browser to raise the default priority up to high for these images so it can start loading much sooner. All right, now we're on LCP phase number 3, resource load duration. This one is also only applicable to LCP external resources like images and videos. It measures how long the resource takes to load from start to finish. And because LCP is measuring the time for an image to appear, it wouldn't be unreasonable to think that the image's download time is usually the bottleneck. And so when talking about LCP optimization, it's easy to jump straight into the things that make the image load more quickly. And we'll get to those things in a second, but I did want to take this opportunity to share some of the important data that my team has just published recently on the most common LCP bottlenecks. In August, my colleague Brendan Kenny published a blog post titled Common Misconceptions About How to Optimize LCP. The URL is in the corner of the slide. I also have a QR code at the end. So I think this chart sums it up pretty well. Let me walk you through it. For every website in the Chrome User Experience Report, we looked at their, it's not yet public, we looked at their data on the 4 LCP phases. We aggregated these phase distributions by taking their 75th percentile, and then aggregated those stats over all 19 or so million websites in the data set by taking the median value of each of those. So it's a distribution of distributions. It's kind of mind-bending, I know. We did that 3 times for websites having origin-level LCP performance of good, needs improvement, and poor. So you can look at this chart and see which phases sites tend to struggle with the most, depending on their LCP performance. And interestingly, you'll find that resource load duration, which is represented by the green bar here, is always the fastest phase. It does get slower as LCP gets worse, but it's still far from the bottleneck. This data is not saying that you never need to worry about image optimization, but maybe what we can take away from this is that images already tend to be optimized well enough that there are other higher priority things that you should be focusing on to improve your LCP. The phases that actually seem to be most worrisome, at least to me, are TTFB in blue and resource load delay in red. And that's why all 3 of the most effective ways to improve LCP so far have been attributed to those phases. That's where websites have the most to gain. All right, so let's say you're one of the few sites that does have terrible resource load duration. How do you fix it? I think you all have heard these answers 100 times before, so we'll just breeze right through this. So you should try using a modern image format like WebP or AVIF to reduce that file size. It's going to speed up the download time as a result. And WebP tends to be about 30% smaller than comparable JPEG or PNG images. You can also reduce the file size by decreasing the image quality by a lot. You don't need to save everything at 100% quality when the human eye can't even tell the difference between that and 80%. You can also scale the images down to avoid wasting bytes on pixels that never get rendered to the user. So even if the image itself is small, there are still some things that you can do to shorten the time it takes to go to the server and back. The best way to do that is to set a long cache lifetime on your images, assuming that they rarely change. So then on repeat visits, users can just reuse what they've already had in cache. And that eliminates that network request entirely. The other thing that you can do to avoid extra connection setup costs is hosting the image on the same domain as your HTML resource. The same things that slow down TTFB can also slow down this image request. You won't need to pay those costs if you use the connections that are already open. Now we're at the fourth and final LCP phase, which is element render delay. When there's an LCP resource, the render delay is measured from the time that the resource is done loading to the time that the resource is finally displayed to the user. And when the element is text, the render delay starts directly from the TTFB time. So as a quick recap of what I've already mentioned before, attempts to minimize the load delay phase might end up shifting the problem to the render delay phase with preloading. Things like CSS background images, client-side rendering, or lazy loading can continue to delay that LCP time in the form of render delay, no matter how early you've preloaded that image. So this is one of the few text-based LCP-specific things to know, and it has to do with web fonts. Fonts are external resources, web fonts specifically, so they show up in the waterfall diagram, but they're not considered to be an LCP resource, so the render delay and loading duration phases do not actually apply. The reason why web fonts matter to LCP has to do with the fact that LCP candidates change over time. So let's say that your initial LCP is an H1 element, and then your super cool custom web font loads a few seconds later. If that web font changes the geometry of the text and bumps the size up just a little bit, that is going to be the new LCP candidate several seconds later. So it could hurt your performance. The best fix for this is to ensure that the system font that's initially shown has a similar size to the custom web font. And you can do that with the size adjust CSS property. There are also ways to speed up your web font so that it doesn't impact the LCP time as much. So fonts should be cached for a long time. A lot of these things are the same things that you can do for images. Cache them for a long time, use better compression, use modern image format or font formats like WAF2. It's an industry standard and it's supported by all modern browsers. You should also, ideally, self-host your fonts. Eliminate that extra connection setup cost. There are services like Google Fonts, and they do offer some advanced font optimization strategies like subsetting. You can say only load the glyphs in this font that are applicable to the characters that I display on this page, like Latin or whatever. You could also subset a font to specific characters. If your heading says hello world, you can only load those letters, H-E-L-L. So finally, the silent killer of LCP performance is slow JavaScript execution. And we don't usually think of this as a loading performance issue, but it definitely could be. And I'm not talking about client-side rendering either. Anything that blocks the main thread for an extended period of time delays the next opportunity to paint. And if the LCP image is downloaded and ready to go, all of this time will be attributed to its render delay. So the solution to this is to break up your long tasks. But that's exactly what I'm about to talk about in the next few slides for INP, so let's get right into it. This is core web vital number 2, interaction to next paint. INP performs really well on desktop. 97% of sites have good INP. 76% of sites have good INP on mobile, which is a little deceivingly high because if you look at only the top 1,000 most popular websites, this number drops down to 63 now. So there is definitely still a lot of room for improvement with INP, despite the gains. This is what a real interaction looks like in Chrome DevTools. The top is the interaction track, and that shows that the user probably clicked on something, probably creating pointer events. And below that is all of the main thread activity during the interaction, with each entry color-coded and labeled according to the type of work that it did. So again, let's simplify this down. The top part is the timing of the interaction using box and whiskers representing the 3 INP phases. And the bottom part represents the main thread activity, JS execution in orange, layout work in purple, rendering and painting in green. All right, so using this diagram, let's jump into the INP phases. The left whisker represents the input delay phase. This is what first input delay used to measure. That's measured from the moment that the user starts their interaction until the processing for that event can start. The central box represents the processing duration. This includes all of the time spent handling one or more of the events associated with the interaction, like a pointer up and a click event of a tap interaction. The right whisker represents the presentation delay. This is everything that happens after the events have been processed until that frame is painted to the screen. So the number 4 most effective way to improve Core Web Vitals affects the input delay phase, but it could also be just as impactful to the next phase as well, and this is to avoid unnecessary JavaScript. You can spend ages shaving milliseconds off of your runtime performance, but it would be so much easier if you could just throw that code away. Remember from the Project Feather story about the tipping point. It came when Chris was able to replace the Flash player with the native HTML5 video player. And thankfully, we don't have to worry about Flash plugins anymore, but we do have a ton of redundant JavaScript on our websites for things like libraries and polyfills. And just for example, CSS has gotten so incredibly powerful in recent years that things like animations could be done entirely scriptless. You don't need to throw everything away either. Even if you just split your JavaScript bundles into things that you need to use now or use later, then you can skip a lot of the time spent parsing and compiling unnecessary scripts. Number 5 is yielding to break up long tasks. And this is listed under the processing phase, but also it could be used to improve the input delay phase as well. So whenever JavaScript is taking a long time to do its work, it's an opportunity to pause, give the browser a chance to paint a frame, and then go back and resume your work. And this is a strategy known as yielding. You do need to be a little bit judicious about when you yield. Ideally, you should do all of the user visible work first, and then ensure those changes are displayed to the user. And for any follow-up work that's needed, like lower priority background tasks, maybe logging to analytics, that stuff that can happen later. If doing lots of little bits of work many times, you could over-yield. Maybe if you're iterating over a large array, you don't want to have your yield statement in that array because there is a little bit of an overhead to seed control and then take it back, and that could add up. Instead, what you want to do is kind of keep track of how long you've been in the loop, yield only if it's time to paint another frame, so tasks should be kept to under 50 milliseconds, and if you're a speed freak and you need to keep a 60 FPS frame rate, then 16 milliseconds is going to be your budget. So if you're looking to yield, there are a couple of APIs in the scheduler API called yield and post task. They're available in Chromium-based browsers, but for everybody else, you can just use a simple set timeout, and that'll usually do the trick. During the presentation delay phase, the browser does all of the required style and layout work to get to the next frame ready to paint. So number 6 is avoid incurring large rendering updates. However, it's possible to incur expensive rendering work during the processing phase when it's forced by JavaScript code. So you've probably heard this referred to as layout thrashing. It happens when you modify a DOM element in one part of your code, and then you try measuring it in a new part of your code. This forces the browser to recalculate all of the styles that are necessary to measure that element, and that takes time. Layout thrashing specifically refers to doing this lots and lots of times over lots of elements, causing a chain of expensive rendering work that blocks the main thread. So you can break that chain by reorganizing your code so that your read operations happen before you modify the DOM. And then any necessary style recalculation work can happen normally during that presentation phase. Routine rendering updates do normally occur during the presentation phase, and there are also some things that you can do to minimize that time. The first is to reduce the number of affected nodes that need to be repainted. For example, changing the class list on the body could invalidate the styles for all of the child elements on the page. And that could be made even more expensive if you have expensive CSS selectors that take the browser a long time to figure out if a specific node is going to be affected by that change. So to mitigate this, you could simplify the selectors, but the most effective thing is just to minimize the number of DOM elements on the page itself. That leads to fewer elements to check and also faster style recalculation times. Another way to minimize rendering time is to lazily render contents that are off the screen using something called CSS containment. The content visibility property just landed in Firefox earlier this year, so now it is available across all modern browsers. You can configure it to tell browsers to skip an element's layout, style, and paint work if it's not visible to the user. And then when the element starts to come into view, the browser can then resume its rendering work just in time. All right, the last metric is cumulative layout shift. It's the best performing core web vital in the wild, and also arguably the most straightforward to optimize. It is kind of a strange performance metric in that it's not measured in terms of time. It doesn't have any units at all. And as a matter of fact, we don't use it to, we don't have any phases to break it down because it's unitless. So for that reason, we're just going to jump straight into the ways to optimize it. With number 7, reserving space for content by explicitly setting its dimensions. So for an image element, you should know how big it's going to be and set its height and width accordingly. Otherwise, if the image has an initial height of 0 pixels while the browser's waiting for it to load, once that pops in, that's going to shift the layout down, causing a jarring user experience. If you at least know what shape the content is going to be, you can use the aspect ratio property in CSS, and then you can dynamically size the content. And in the worst case scenario, if you have no idea what's about to happen, you can at least reserve a little bit of space using the min height or min width attributes. There might still be a noticeable shift, but at least it won't be as severe. This one might come as a surprise, but number 8 is actually to take advantage of the BF cache, which we've already talked about as an LCP optimization. The reason why this is a game changer for CLS is because a significant amount of the layout shifts that happen actually occur during the initial page load. So when you restore a page that's already been loaded and already been rendered, any of those layout shifts will have already happened, and so the new page view will appear much more stable. But today, the biggest blockers to BF cache eligibility are listening to the unload event and also serving HTML resources with the cache control no store header. So finally, number 9 is to optimize CLS by avoiding layout-inducing CSS properties in animations and transitions. So for example, if you want to slide a piece of content down, you might be tempted to animate its down property. But even if the content is on its own layer, changing the property actually triggers layout work. The other directional properties like up, left, and right behave exactly the same way. And the solution to this is use CSS properties that are animated by the compositor thread instead. That means using things like transform, translate Y to move things. And these types of animations do not incur any layout shifts. All right, we've covered the core web vitals themselves, so I'd like to use whatever remaining time I have to talk about the data that goes behind it. I think most of you are familiar with the Chrome User Experience Report, or CRUX dataset, but I did want to highlight one really important distinction. CRUX powers Chrome and search tools like PageSpeed Insights, DevTools, Search Console. It's Chrome's source of truth for how fast or slow users are experiencing core web vitals. It's an incredibly powerful data set, but the kinds of questions that it's designed to answer are actually pretty simple. Like, do 75% of the experiences meet the good threshold? Yes or no? How about this metric, or this form factor, or this page? It's not designed to answer the second most important question, which is, okay, so why was it slow? For that, you need diagnostic tools. Lighthouse is a diagnostic tool, and it can point you in the right direction, but it can't tell you why your users' experiences were slow. It doesn't know how users access or behave on the page, and it doesn't know what their LCP elements tend to be. But these are all things that you can measure yourselves, and the name for that is Real User Measurement, or RUM. This is something that each site will need to instrument themselves using a commercial RUM product, assuming they have Core Web Vitals support, or some kind of homegrown solution. But the data is worth its weight in gold because you can use it to understand why things are slow and how to reproduce them. Data is also really hard to argue with. You might recommend to a client that they should consider cleaning up some of their marketing tags. The pushback usually sounds something like, but we need those. Well, then you can come back to them with data to say, such and such a tag typically adds 250 milliseconds to every click on the page, and it's robbing you of a good INP score. Well, maybe they'd change their mind. The other thing that's great about RUM data is that you can measure the impact of your changes, ideally with something like an A/B test, but even just watching the change over time is really, really great. Crux data moves very slowly. It's a 28-day aggregation, but RUM data, on the other hand, you can slice it any way you want. And when you correlate that with other business metrics in your analytics, you can paint a really compelling picture about the impact that you're having and how valuable your work is. Just to give you an idea of what's possible, and this is using all free Google tools, this is a dashboard that I built to diagnose INP issues on our web.dev website. It uses the attribution build of the open source Web Vitals.js library to measure the user experiences and get diagnostic data about it. I send that off to Google Analytics using custom events. I process all of that data on BigQuery, and I visualize it in Looker Studio. So for example, I can use this data to track INP performance across the entire site or groups of pages. I plot it out over time or as a full distribution, and I can drill down into the most popular and problematic areas. In this case, it looks like the learn pages are especially slow. So I can explore the INP phases to see where the time is spent and what is causing it to be slow. I know it's hard to draw any kind of conclusion from this at a glance, but this data did help me understand that there was something other than script processing time that was slowing down interactions. The input and presentation delay phases were much slower. So I dug deeper into what users were interacting with and when. I found that the most common interactions were kind of confusing. Users were just clicking on text. That's not very interactive, but something was still causing that to be slow. So the dashboard gave me all of the information I needed to build a reproducible test case so I could figure it out locally in DevTools. So I loaded up the page, I started to trace, I clicked on the heading text, and here's what I found. And just like in the RUM data, there was a relatively quick processing duration with those long whiskers extending outward, indicating a slow input delay and presentation delay phases. There seemed to be a lot of expensive style recalculation work happening, and DevTools helped me trace it back to animating spinners. I hope this video loads. Yes. So I thought that was really weird because I didn't see any spinners on the page, but sure enough, they were still there, animating away. In fact, I found 31 spinner components on the page, all stuck in an infinite loop. And the problem was that despite being hidden, the animations were not paused. Pausing the animations was a simple enough fix, so we pushed it live, and we immediately saw a 25% improvement to our mobile INP across the learn pages. So we still have more work to do, getting our INP closer to the green, but we are making progress, and it wouldn't be possible without RUM data to guide the way. So while it's true that all of you in the SEO community are focused on succeeding in search, we're still very closely aligned with our goals with the web performance community to improve core web vitals. I hope I was able to show you that web performance, I was able to show you web performance in a slightly different light, and also how your work to improve core web vitals improves the speed of the web as a whole. I also hope that you take these things that you've learned about Core Web Vitals metrics and the most effective ways to diagnose and optimize them, and you do what you do best. Share it with the community and apply it in practice to help make an even faster web. Thank you.
Give it up one more time.